This invisible gas lights up entire cities, but it almost never reacts with anything. Meet neon, the noble gas behind quietest element with one of the brightest impacts.
So if you just take a second and look at the device you are using right now, like your phone or your laptop, the microscopic pathways powering its processor, the very architecture that allows it to even function, were carved by light.
Right, not just ambient light either.
Exactly. We're talking about an invisible, deep ultraviolet laser beam. And it's born from a gas that adamantly refuses to react with, well, pretty much anything on Earth.
Which is just wild when you think about it.
It really is. We are talking about element 10, neon. And welcome to today's deep dive, where we're unpacking a really fascinating stack of research titled Neon, the Noble Glow of Modern Technology.
Yeah, it presents this incredible paradox, doesn't it?
Oh, totally. Because on one hand, you have this entirely stable, invisible, unreactive ghost of a gas. It just floats through the atmosphere, completely ignoring the rest of the periodic table.
Just minding its own business.
Right. But then on the other hand, without it, our most iconic city skylines would go completely dark. They'd lose that signature glow. And even crazier, the global semiconductor industry would just grind to an absolute halt.
It would completely freeze up.
So our mission today is to figure out, how can an invisible gas create some of the brightest lights on Earth? How did this chemically aloof element become the hidden engine of the modern digital age?
Well, the contrast is really what makes element 10 so compelling to study.
Yeah.
I mean, you have a substance defined by its absolute chemical apathy.
Apathy is a great word for it.
It is, because it has a full valence electron shell, rendering it perfectly content in its quantum state. It does not burn, it doesn't corrode, and it forms basically zero stable compounds under normal conditions.
So it's just perfectly inert.
Right. Yet, as our sources highlight, that specific unreactive nature, that total thermodynamic stability, is precisely what allows us to harness its physical properties. It's how we push the boundaries of modern engineering.
Okay, but before we can even understand how we use it to build, AI processors today, we really have to look at how we managed to find it in the first place.
Yeah, which was not easy.
I mean, it sounds like a metallurgical and chemical nightmare. Hunting for a gas that is invisible, odorless, and just totally refuses to bind to anything else.
It's like looking for a needle in a haystack, but the needle is invisible.
Exactly. So the research takes us back to 1898, right? To the laboratory of chemists William Ramsay and Morris Travers in London.
Yes. And they were essentially flying blind.
They were just looking for gaps in the periodic table, specifically searching for those missing noble gases between helium and argon.
And their methodology was just this grueling thermodynamic slog. I mean, they had to rely on the fractional distillation of liquid air.
Which sounds so intensely complicated.
It is, yeah.
Yeah.
To do this, they took massive volumes of normal atmospheric air and they subjected it to immense pressure and extreme cold.
We're talking like dropping the temperature down to nearly minus 200 degrees Celsius, right?
Exactly. Right down until the air physically condensed into a liquid.
Oh, wow.
And then once they had this super-cooled liquid air, they painstakingly allowed it to warm up just degree by degree.
Because different gases have different boiling points, right? So they were just waiting for the unknown elements to boil off and separate out one by one as it warmed up.
Yeah, that is the mechanism. Nitrogen and oxygen boil off first.
Makes sense, since that's most of the air.
Right. And they had already isolated krypton this way, but they knew mathematically that something lighter had to be hiding in that remaining fraction.
But when they finally isolated this specific lighter fraction, they still couldn't see it.
No, it was completely invisible.
So the only way to confirm they actually had something new was to put it inside a sealed vacuum tube and run a high-voltage electrical current through it, just to analyze its emission spectrum.
And the accounts from Travers about that moment are almost poetic.
Yeah, he wrote that the moment they applied the voltage, the tube blazed with this fierce, brilliant crimson-red light.
I think he called it a sight to dwell upon and never forget.
Which is just so cool. And they named it neon, derived from the Greek word neos, meaning new. But, the irony is that it was hiding in plain sight all along. It wasn't new.
No, it was just perfectly insulated from the rest of the chemical world.
Right. And that insulation, it all comes down to its quantum architecture, right?
Exactly. With atomic number 10, neon's outer electron shell is completely filled with 8 electrons.
So it's totally full.
Yeah, it is the textbook definition of chemical equilibrium. I mean, most chemical reactions are driven by atoms desperately seeking that exact state. They will violently share, steal, or discard electrons just to achieve a stable octet.
But neon is just born with it.
Right.
I like to visualize this chemical aloofness using like a party analogy, but specifically thinking about the energy dynamics.
Okay, I like where this is going.
So most elements in the room are highly energetic, right? They're constantly mingling, desperately looking for a partner to stabilize their energy state. They're forming bonds, creating chaos, dropping glass.
Causing a mess.
Exactly. But neon is that guest standing in the corner holding a perfectly balanced plate and a full drink. They are already perfectly content.
They don't need anything from anyone.
Right. They have absolutely no reason to mingle, react, or form bonds. They won't take anything you offer, and they won't give anything away.
And what's fascinating here is that this exact chemical stubbornness is its superpower.
How so?
Because it refuses to engage in electron exchange, you can subject neon to incredibly hostile environments. Extreme high voltage, intense cold, or proximity to highly corrosive halogens.
And it just doesn't care.
The neon will simply remain neon. It maintains its structural integrity, where almost any other element would break down, oxidize, or just explode.
Okay, so if we accept that neon is this chemically inert, perfectly content loner that refuses to interact with its surroundings, the obvious question is, how does it manage to put on such a flashy, bright light show?
Right, the glowing signs.
Yeah. We see it in Vegas, Times Square, Tokyo. It defined like entire cyberpunk aesthetics. The glow is iconic. But if there is no chemistry happening, no reaction, how do we get the light?
So the illumination is a purely physical phenomena. It's driven by quantum mechanics, not chemistry.
Okay, break that down for me.
When you trap pure neon gas inside a glass tube at low pressure, and you apply a high voltage current, you are basically bombarding those unreactive atoms with kinetic energy.
Like blasting them with electricity.
Exactly. The electricity forces the electrons out of their comfortable, stable ground state and literally kicks them up into a higher energy orbit.
The excited state.
Right. But because of that inherent drive for stability we just talked about, they can't sustain that high energy orbit for more than a fraction of a second.
They hate it up there.
They really do. So they immediately collapse back down to their ground state. And physics dictates that energy cannot be destroyed, only transformed.
So the energy has to go somewhere.
Exactly. When the electron drops back down to its original orbit, it has to shed that exact quantum of kinetic energy it just absorbed, and it releases that energy as a photon.
A particle of light.
Yes, and for neon, the specific energy gap between the excited state and the ground state corresponds to a photon with a wavelength of approximately 632.8 nanometers.
Which puts it squarely in the vivid red-orange section of the visible light spectrum.
Exactly, and you have millions of atoms undergoing this excitation and relaxation process billions of times a second, creating this continuous piercing glow.
It's just incredible, and that specific, brilliant wavelength totally transformed advertising and pop culture. But our sources actually highlight a really surprising fun fact that I found hard to wrap my head around.
Oh, about its rarity.
Yes. Despite completely dominating our visual landscape for a century, neon is exceptionally rare. It makes up less than 0.002% of Earth's atmosphere.
It's staggering. Its cultural ubiquity completely masks its physical scarcity.
It really does.
I mean, capturing it requires massive industrial air separation units. Usually these are attached to large-scale steel manufacturing plants, processing millions of cubic feet of air just to extract a tiny usable fraction of neon gas.
Wow. And, that scarcity leads directly into one of the biggest misconceptions we need to address. Because I was reading the sources and I saw this, and wait, let's unpack this for a second.
Let's do it.
Are you saying that when I walk down a rainy street and I see a bright blue or green quote-unquote neon sign in a diner window, it's actually a lie? Like, chemically speaking.
Chemically speaking, yes. It is a lie.
That's crazy, because if neon only emits photons at that 632.8 nanometer wavelength, that orange-red, then those other colors can't be neon.
You're completely right. The term neon sign has just become this semantic catch-all in pop culture that completely ignores the actual science.
So they don't contain neon at all.
True neon signs strictly emit that signature orange-red. The vivid colors you see in other quote-unquote neon signs are actually created by exciting entirely different noble gases.
Okay, so if I'm looking at a bright blue sign, what am I actually looking at?
Blue is typically achieved using argon gas.
Oh, interesting.
Yeah, often they combine it with a tiny droplet of mercury to intensify the ultraviolet emission, which then reacts with the phosphor coating on the inside of the glass tube to make it really pop.
What about other colors, like that pale purple or white?
A pale lavender or purple glow is usually helium. and a stark silvery white is often krypton.
So the underlying physical principle is identical, bombarding a gas with electricity to excite the electrons. But the specific atomic structure of the gas dictates the color.
Exactly. Different quantum architecture means different energy gaps, which results in entirely different wavelengths of light.
Okay, so that exact ability to harness a specific pure wavelength of light from an excited gas that didn't just stay in diner windows.
No, it scaled down dramatically.
Right, to the microscopic level. It basically became the backbone of the most advanced technology you own. And this shifts us from retro pop culture straight into cutting-edge tech. We are talking about excimer lasers.
The excimer laser is really where neon's chemical stability is pushed to its absolute industrial limit.
So what are these lasers actually used for?
These lasers are the true workhorses of semiconductor photolithography. When manufacturers are designing the microchips for your smartphone, or those massive processors required to train AI models, they are trying to print billions of transistors onto a single silicon wafer.
Billions, that's just wild.
It is. And you cannot physically carve or etch patterns that are only a few nanometers wide. You have to use light to project the pattern onto a photosensitive chemical layer on the silicon.
And visible red light from a standard neon tube isn't going to cut it, right? Because the wavelength is way too wide.
Exactly.
I mean, a 632 nanometer wave is basically a blunt instrument when you are trying to carve a 5 nanometer transistor. You need a much tighter, shorter wavelength to get that microscopic precision.
Right, and to get that ultra-short wavelength, you have to move out of the visible spectrum entirely and go deep into the ultraviolet.
Enter the excimer laser.
Right. Excimer is short for excited dimer. Inside the laser cavity, you have this highly pressurized mixture of a noble gas and a very reactive halogen gas. A common configuration is argon and fluorine.
Okay, wait, I need to jump in and ask a question here.
Here, go ahead.
So what does this all mean for the device you're holding right now? Because we've spent this entire time talking about neon as the anchor of this tech. But if the laser is using argon and fluorine to create the deep UV light, where does element 10 actually fit into this process?
That is the crucial part. Neon is the buffer gas, and it actually makes up more than 95% of the gas mixture inside that laser cavity.
95%?
Yeah. Argon and fluorine are the active ingredients that actually form the temporary molecule, the dimer, that emits the ultraviolet photon. But you can't just fill a tube with argon and fluorine and hit it with raw electricity.
Why not?
Because fluorine is wildly reactive.
Yeah.
The energy transfer would be super inefficient and chaotic, and it would likely just destroy the laser cavity from the inside out.
Oh, I see. So I like to think of this ultra-pure neon in an excimer laser as like an incredibly precise microscopic scalpel made of pure light carving the brain of your smartphone. But to make that scalpel work, the neon has to be the kinetic conductor.
That is exactly it. Because neon is so dense and perfectly stable, it acts as this ultimate thermal and kinetic buffer.
So it absorbs the shock.
Right. When the high-voltage discharge hits the gas mixture, the neon absorbs the brunt of that massive electrical energy and efficiently transfers it to the argon and fluorine atoms without ever chemically reacting with them.
Wow. It just orchestrates the whole quantum dance.
Yes. It allows the active gases to form the excited dimer and release that precise deep UV light while keeping the internal environment of the laser completely stable. Without neon-specific light-emitting properties and stability, producing the complex chips required for modern AI would literally grind to a halt.
Which makes perfect sense. Without neon acting as that perfectly insulated mediator, the laser would burn itself out. We wouldn't have the deep UV light required to carve modern semiconductors.
You'd be stuck in the past.
Right. And this leads directly into a very real geopolitical and economic reality that our sources detail. The global supply chain for this ultra-pure semiconductor-grade neon is, well, it's incredibly fragile.
It is deeply fragile, and a lot of that stems from the extreme purification required.
Because it's not just regular neon.
No, not at all. Taking neon from a standard purity of, say, 99.9% up to the 99.999% purity required for photolithography, that requires highly, highly specialized infrastructure.
And I imagine if you get it wrong, it's a disaster.
Oh, yeah. If you introduce even a microscopic amount of contamination into an excimer laser, it alters the light's wavelength slightly. And a multi-million-dollar batch of silicon wafers is instantly ruined.
The stakes are just astronomical. If a major global supplier of highly purified neon goes offline, the bottleneck is immediate.
We saw it happen recently. Global neon shortages severely affected semiconductor and electronic supply chains worldwide.
Because you can't just substitute it, right? Like you can't just throw argon or helium in there as a buffer instead.
No, you can't. The thermodynamics of the laser require neon's exact atomic mass and thermal conductivity. Without it, the production lines for everything from, automotive microcontrollers to high-end AI processors simply stop running.
It really underscores this fascinating vulnerability in our modern technological stack. Trillions of dollars of digital infrastructure are totally dependent on a continuous supply of a gas that makes up a fraction of a percent of the air we breathe.
It's humbling, really.
It is, but the utility of element 10 isn't just confined to high-energy lasers or glowing signs.
No, it has other incredible uses.
Right, and here's where it gets really interesting in the research. How can the exact same element be responsible for both high-energy, fiery-looking excimer lasers and cryogenic refrigeration?
That is the beauty of its extreme chemical stubbornness. It makes it equally vital at the totally opposite end of the thermodynamic spectrum, the realm of absolute freezing.
Okay, explain how we use it to freeze things.
Well, when you cool neon down to minus 246 degrees Celsius, it condenses into liquid neon. And as the cryogenic refrigerant, it possesses physical properties that make it far superior to liquid helium or liquid hydrogen for certain high-stakes applications.
Really? Because we hear about liquid helium all the time, right? Like for cooling MRI machines or superconducting magnets. Why is liquid neon a better option sometimes?
It mostly comes down to density and the latent heat of vaporization.
Meaning how well it absorbs heat before boiling away.
Exactly. Liquid helium is incredibly cold, but it is extremely light, and it boils away rapidly when exposed to heat. Liquid neon is much denser. It actually has over 40 times the refrigerating capacity per unit volume than liquid helium.
Oh, wow. So it can absorb a massive amount of thermal energy before it transitions back into a gas.
Right. So if you have a highly sensitive scientific instrument or a supercomputing array that requires absolute thermal stability, liquid neon acts as this massive, reliable thermal heat sink.
And because it's a noble gas, if there's a leak, it won't spontaneously combust like liquid hydrogen might, right?
Exactly. Because it has a very low boiling point and is a monatomic gas that won't corrode or react with machinery, it's the perfect, safe, inert medium for industrial safety.
So it's safe to use.
Mostly, yeah. It won't explode. It won't form ice blockages in the piping.
Yeah.
The only environmental or safety hazard associated with neon relies purely on its physical mass as an asphyxiant.
Right. Like if you are in a sealed laboratory in a high-pressure tank of neon ruptures, the gas itself isn't toxic. It doesn't poison you.
Right, it doesn't damage the ozone layer either.
But it will rapidly displace the oxygen in the room. So the danger is you would suffocate simply because the neon pushed all the breathable air out of that confined space?
Yes, but as long as it's handled properly under normal conditions, it is fundamentally benign and environmentally safe.
And that benign, stable nature is also what allows astrophysicists to use it as a foundational tool for basically understanding the universe.
Yes, moving out into the vast emptiness of space.
Right. The applications for neon extend far beyond Earth's atmosphere and deep into the cosmos through the science of spectroscopy. And this is where the research gets incredibly profound to me.
That's one of my favorite parts.
We established earlier that when you excite a neon atom, it releases a photon at a very specific wavelength. Well, it turns out that specific wavelength acts like a cosmic barcode.
It does. Every element on the periodic table has a unique emission and absorption spectrum.
So when astrophysicists point space telescopes at distant stars or nebulae, what are they looking for?
They capture the light across massive distances and run it through a spectrometer. They're looking for specific dark lines in that spectrum. They're called Fraunhofer lines that correspond to the known wavelengths of elements, like neon.
So they aren't sending probes to these stars. They are literally reading the signature of the light itself.
Exactly. When they spot that 632 nanometer signature, they know, without a doubt, that neon is present in the stellar atmosphere.
But how does neon even get into a star millions of light years away? I mean, we extract it from air here on Earth.
It's forged in the core of massive stars through stellar nucleosynthesis.
Okay, so the star is actually making the neon.
Yes. During the later stages of a star's life, specifically during what's called the carbon burning phase, the immense pressure and temperature cause carbon atoms to fuse together, producing neon.
That is wild.
And by measuring the concentration of neon in a star's spectrum, astrophysicists can determine the star's age, its mass, and exactly how far along it is in its evolutionary life cycle.
So we are using the exact same quantum mechanical principles that light up a retro diner sign in Chicago to map the life cycle of a supergent star in another galaxy.
It is a brilliant symmetry, isn't it?
It really is. And it just proves that neon isn't just a nostalgic relic of 20th century advertising, nor is it just a temporary solution for today's semiconductor manufacturing. It is a fundamental baseline for human discovery.
Absolutely. And looking forward, the demand for that perfectly stable baseline is only going to accelerate.
What does the future look like for element 10?
As we look toward next-generation semiconductor manufacturing, advanced photonics, high-efficiency laser systems, and quantum technologies, the engineering tolerances are becoming almost unimaginably tight.
I mean, we're already carving nanometer-scale transistors. What's next?
We are moving toward manipulating individual photons and delicate quantum states. And as scientific instruments become more precise, the need for a perfectly stable, unreactive baseline environment grows.
Because the more precise our ambitions become, the more we require an environment completely free of chemical interference. We need an element that absolutely will not disrupt the delicate quantum architecture we are trying to build.
We need our perfectly stable, unreactive guest to hold the thermodynamic space.
Exactly. It's such a great irony, Think about it. An element defined entirely by its refusal to change or interact with anything is precisely what is driving the most rapid technological changes in human history.
That is perfectly said. It provides the inert scaffolding. You simply cannot build highly complex, hypersensitive technological systems in an environment prone to spontaneous chemical reactions. Neon's refusal to change is the anchor that allows everything around it to advance.
Which perfectly encapsulates the core takeaway we can draw from this entire stack of research today. Element 10 is the ultimate silent partner.
It really is.
Neon doesn't change itself. It helps illuminate and enable the technologies that change the world.
I love that. It's the invisible medium translating human ambition into physical reality, whether that is through microscopic photolithography or massive stellar spectroscopy.
So the next time you pick up your smartphone or you read about an amazing new AI breakthrough, or you just walk down a rainy street and see that warm, piercing red glow in a window, remember that you are witnessing the quiet, unyielding power of element 10.
And it leaves you with a really fascinating reality to mull over, especially when you think about the vast space exploration and atmospheric research we just talked about.
What's that?
Well, if the entire architecture of the digital age and the future of quantum tech and our understanding of stellar evolution, if all of that hinges on a completely invisible gas that makes up less than 0.002% of Earth's atmosphere, what other incredibly rare, seemingly useless, or invisible elements are currently floating all around us? Just waiting for the right spark of electricity to unlock the next century of scientific breakthroughs.